So, hello and good morning, everyone. Thank you, Ali. I'm not sure if Ali is there for laying out the foundation as well. Whoever were not there yesterday, just to give you a highlight, what Arena 2036 is, we are a research campus, active research environment for next generation of automobiles, and 2036 is a number for the 150th anniversary since the first patent was filed by Mr. Carl Benz as a gas engine. So what we are talking about today, why classical AI faces limit, what quantum improves the advantage, and then how the practical middle ground is, what hybrid is to combine the quantum efforts with the classical approaches, and then all the 5 benchmark models that we have. I will try to give you an overview, a really quick overview of how we are working with different classical AI methods, including the convolutional neural network, then the QAN, that's the quantum convolutional neural networks. Then Ali already laid down the foundation with the GAN approaches as well, because for the industrial perspective, the GAN, these generative adversarial models are very much important, what we have observed. Then with variational quantum circuits, support vector machine, and with classical encoders and quantum encoders, and then I will try to end up my presentation with 2 of my students, how they are applying these classical approaches into an actual robotic industrial use cases. Motivation, obviously, including the data dependability. The major question is how we are going to take care of huge amount of data sets. Not every use case should use quantum computing, as already Ali said, the computational time. How we will work from CPUs to GPUs to HPCs to QPUs now. That's what we are trying to work on. But then the scalability and reliability, handling the data complexity as well. And then how we are trying to provide these robustness to the tools to provide a solution to the industry. Since Arena, we have 70 partners, all the industrial partners, so we are relatively having different use cases as well. So, I really like, what's the advantage of computers? We'll be able to solve certain problems in seconds. That would take the age of universe for classical computing. Yes, obviously it's bookish, more theoretical. But yes, existing research demonstrating quantum benefit, solving linear systems equation, regression analysis, quadratic, polynomial equations that could actually maps a complete provide separations in feature space, not efficiently, but replicated classically. The idea is not to disregard the complete perspective of AI, but to bring quantum together with AI. Don't confuse, quantum machine learning is not a big hype. It's just adding some quantum layers, qubit layers, into your actual classical machine learning model, or to deploy it on a quantum computer. The question is, do you really think the true challenge is building better quantum computer, or asking the right question that they can answer? Let's see, the advantage of having a quantum reality, or in AI, is like, obviously, massive parallelism from superposition that gives an ability to represent the data exponentially. Solve that. Computational speed-ups, yes, but no one talks about the energy efficiency that we are going to combine. Quantum circuits can explore distributions, yes, and that may be hard classically in generative tasks. Then, as I mentioned, noise data, including integrating noises into the different data sets. Then GPUs, different kind of TPUs as well, the terabyte processing units. We are talking about gigafactories and lots of things. And then, as already mentioned in one of the slides previously by Ali, how we could take care of the error corrections, having the stability, because it's just the foundational basis that what we are talking about. What does really hybrid means? To bring AI and quantum together, having a pre-processing unit, having a quantum layer or a quantum system, adding that layer onto the quantum hardware, and then having a post-processing. Why not just use a classical system from AI? And then, okay, it doesn't want to go. Oh yeah, sorry. So why is this promising for AI? It actually enables leverage quantum advantages where it matters, scalabilities, moving around with the data sets as well. Early research, you can find it in the literature research, that how hybrids can improve the generalization, because that's what the industries are looking for. Artificial intelligence applied to a complete laptop cannot actually apply to your computers. It varies from case to case. It varies from different data set to data set. And then, what are we, or from Arena, from the method or model-based design systeming approach, what we are trying to do is We have a simple quantum machine learning pipeline. We have data silos. We have a data cleaning, data extraction. This is what all we are doing in a general purpose AI models. And then comes the parametric part of the optimization, varying, tweaking the important parameters to have the results. But this is where the quantum machine learning or quantum pipeline comes up, where you can actually classify which data needs to be treated as classical AI, which needs to be treated with the quantum layer, and then try to converge them to avoid high dimensionality running parts in the quantum world. Now the QML approaches, I will quickly try to get you through with the method-based design approaches with QCNNs, QNNs, variational quantum circuits, QGANs, and the autoencoders as well. You already had some idea from what Ali presented. So when we talk about convolutional neural network, is the future of image recognition about adding more layers or adding more dimensions? Obviously, that's how the pictures are actually adding it up. The concept, a simple concept, we have a feature extraction. We have a picture, any image. X-arrays, or actually the color-based feature extraction as well. Having the whole idea, and then already explained by the previous speaker about these qubits, these binary digits, and how we could have these convolved feature into that. And at the end, we have the whole pooling approach. This is all the computation that's working on. And then, why do we need to have a quantum-enhanced convolutional neural network? Yes, it could actually encode images into the high-dimensional Hilbert spaces, capturing richer correlation, bringing in the aspect of solving this computational effort, and then mimic these structures, having a good advantage of improving these generalizations, just varying the parameters and get the result at the end to provide the robustness. Yes, we are still working to find a good way to integrate and play around with the noises. Kaggle, all open source data, being the basics, laying the foundational levels, how the MNIST digit data set is, brain tumor classification. This is actually synthetically generated in-house, all the defects, scratches, microscopic defects, macroscopic defects that are really, really important when we talk about the industrial products. So, simple methodology. Synthetically, we generated the data set. The data set that we have is around 8,500 images. The actual images that we took were around 4,700. Then we extrapolated these defects. What kind of defects? Scratches, pores, gaps, lots of different defects. And then we added a quantum convolutional layer. Divided them into the patches as well. One of the students, Ananya, she's already working in her master thesis on this, and applying the classical neural network approach into this whole regime. And at the end, we have trainings and results. Yes, we had good, improved results. But this is just, again, a beginning of laying down the foundations. Then MNIST datasets. We all are aware of the MNIST datasets. They're all open source, different regimes, different classification, good results on the tabular, comparing the QNN's model, benchmarking them with CNN, and then we try to analyze the results as well. Working with the brain tumor classification as well, image-based dataset with brain tumors. Performance matrix. The idea is to show that yes, quantum has a good advantage over classical AI, and if we add some quantum layers, yes, the limitation is if we deploy these on a quantum hardware, everything will drastically improve as well. Yes, that's a possibility. And then synthetic defects dataset. Obviously, that's a bit important for the industry. And yes, in this case, the classical outperforms quantum. Not every dataset should be treated using a quantum layer approach. We tried different approaches. Initial results, as you can see, that it showed that CNN outperformed the QSCNN in terms of performance. And obviously, further testing and improvements will definitely provide a better evaluation of results. The power of imagining AI into the generative adversarial network, having ready to simulate CAD geometries into the industrial aspect is a bigger question than what we are trying to solve using CGAN, that's a classical GAN, and QGAN, that's a quantum GAN. Having a complete generator, real samples, discriminator, having fine tunes, and then why do we need GAN, QGANs at the end? Yes, classical GANs actually struggles with mode collapse, having limited diversity in generating the huge amount of data, computational issues. And in contrast, quantum circuits can actually explore richer, denser probability distributions via superpositions and entanglements. That could be one of the overview of how the quantum GANs are working with preprocessing until the comparison with the real data. You can take into account the step files. Lots of industry people, we love to work with CAD data, with step files, with FLS files, with IGS files, point cloud files. These are all could be TXT files, all could be extracted, or could be worked around with this approach. A simple methodology, how a quantum generator works, that could transform random noise, that we are the ones who are generating these random noise, into the candidate data sample, something meaningful. And then the classical discriminator, again, a classical approach, how we are trying to build this bridge with the neural network approach, and then feedbacks on the updates quantum circuits parameters with the classical approach. Just look at the MNIST data set, look at the digits. That's what the classical GAN does, and this is how the output images with the QGAN layer, just integrating the quantum layer. And then working with the pulmonary chest disease data set. We had around 805 images of the chest X-rays, open source data. And then we tried to compile these to 1 to 100 iterations. Hello? Okay. So variational quantum circuits can be programmed with fixed algorithms. What happens when they start learning their own rules? That's the adaptive thing that we are looking for. Just a simple overview of how the classical ML and quantum ML is with qubits and VQC, support vector machine. In Arena, we are trying to implement support vector machine in a 7,000 square meters shop floor to identify thousands and thousands of objects statically and dynamically that we have in our shop floor. That would definitely follow up in the next months if you stay in contact with different conferences and journal papers. Again, how VQC works, you have an input data, more or less you get an idea how the pre-processing, post-processing works, and then we have a layer in between. Then a simple comparison with, again, a data set with VQC in a CAN bus intrusion detection, and we will see the data set B with the engine fault detection. And you can see this is a classical SVM approach, and we have a VQC with a variational quantum circuit approach. Test accuracy 70%. We have an F1 score of 70% around, and we have different. It actually shows how fluctuates and decreases over the training, depends on the integration, the environment that we have created. Then again, a performance gap. You can see it actually achieved 80% compared to VQC 70%. Another data set where the classical outperforms the quantum one. It's still stronger for this data set. Again, this is the one that I mentioned in the first slide, data dependability, data set dependence. And then again, an engine method where you can actually see the test accuracy is around 60%. And over here, the VQC, in this case, VQC performed better as compared to the classical approach, which is both models struggled. But again, better computational efforts and now come back to the routine task with lots of tabular data as well. When applied to everyday data science industry, spreadsheets, planning, we have been in different sessions. Everyone talks about scheduling, planning. What, how, where, why for QNNs? Why? Yes. What? They are just machine learning that integrates quantum circuits, not a big hype. How? They just process the data using quantum circuits. It's not a big deal, not a big science. Where? Used in healthcare, finance, you already saw the example in the previous slide, cybersecurity, image-based data sets, quality inspection, lots of different. And why? To have a leverage of quantum superposition and entanglement, having this layer to improve the computational effort. That's a simple QNN architecture, how the data set is, pre-processing, quantum circuit, and then post-processing. And then we will see how the results outperforms in the simple tabular regression. And this is just one example. We have many, many different use cases into the tabular. Like this is just one of the data set from the health analysis. And then we have the accuracy, which actually demonstrates a robustness and reliability, how it could be useful for the tabular data set. So the accuracy we achieve with QNN can also be achieved using CNN. Yes, just a small difference. With the classical filters and convolutions on data, and then data handling as well, how QNN could be used for high-dimensional small data sets, problems, and complex correlations. Obviously, a good future potential is coming up with mature, optimized, and widely deployed real-world application. That's what we are dealing with in Arena. So then the quantum autoencoder architecture, I'll try to quickly go through this thing, but definitely we could discuss how the whole architecture is working, how we are trying to build up this Q, that's quantum, AI, artificial intelligence, and X, the method-based design approach. Please stay tuned to that, and how the whole VQC approach is working. And then the mathematical model, everything is available, how we are trying to compress the n-dimensional into the latent space, maps into the qubits, and then try to compress this d-dimensional circuit into the d-dimension that could actually reconstruct the whole image. That's some of the examples that we generated. So does benchmarking reveal quantum superiority, or does it remind us how far we still have to go? Just some key takeaways before I hand over the stage to the students. How we are working on different complex data sets, faster training, efficient on simple data. Yes, we also need to take in account on how the computational efforts are. With GPU accelerations, image realism, then VQC versus SVM, how we are working on this, testing on different complex data sets. Then QNN versus CNN, faster learning on small complex data. Then CNNs are reliable for large data sets, yes. Optimized circuit depth and qubit usage. Then, hello, okay, yes. Then it discards redundant qubits, keeps, and then compresses data effectively. That's all theory, all the state of the art. That's the conclusion that we have from our algorithm. Okay. So I will hand over just a quick 2-minute, 3-minute pitch to Ananya and Kanak, who will share their insights. That's the next. That's the next.
Hello. Am I audible? Okay. Thank you, Mohammed. So I'm happy to present my results on quantum GANs or QGANs. We know that defects in manufacturing directly affect the product quality, and traditional AI methods do work well, but require large data sets. And now, given in manufacturing, this is quite rare because these defects are less, and that's why we need QGANs to generate more realistic and smoother images. Now, coming to the pipeline, we first start with the data collection, where we use the NEU surface defect data, and then we pre-process the images with 32 into 32 batches. The next step is training the GAN. We train with the classical baseline and the quantum model. For the classical, I use the conditional GAN, and later we evaluate its performance. Coming to the data set, we mainly grouped into two. That is G1 for surface and G2 for indentation. We wanted to see how the improvements are looking in both the groups. Here are the results. The blue is the without the quantum layer, and the orange is with. So we can see that the baseline doesn't perform so well, but in quantum, we can see that it stabilizes much better in the earlier epochs. Now, we also wanted to see how it varies in the pixel intensities. So we can see that in the baseline, it's quite sharp, noisier, but when it comes to the quantum and basically the indentation defects, it's quite better and smoother in generating these images, and it's more stable. Thank you. Over to Kanak.
Hello, everyone. So my name is Kanak, and thank you, Ananya and Mohammed, for your presentation. So basically, I'm working on a project based on reinforcement learning. So I just want to know how many of you know about reinforcement learning here? Okay, great. So major crowd knows about it, thank God. But then for those who don't know about it, I'll just give you a short overview about reinforcement learning. So say you are in a particular state and you want to go to a next state. Like there are a kind of sequence of states given to you, and you want to choose the next right state for yourself, then you actually use reinforcement learning for that in layman language. So basically, I have been working on the KUKA robot, which is one of the robots which we have right in our workplace, and we are actually using this robot to train our models on. So basically, I am particularly focused on path planning algorithms. So I'm actually trying to train my classical reinforcement learning on that first. And I'm just trying to work on various paths. Like we have square, circle, triangle, all these basic shapes. And then I'm advancing to more complex shapes so that it can trace a good path. And after that, I have been also focusing on training quantum reinforcement learning on that, just to make sure that, just to check how things work out, how better is quantum than over RL algorithm. And what I think is that quantum RL is actually having good convergence. It is having good stability at the end than classical RL, which I'll be showing in the further slides. And talking about the use cases, obviously, it's actually a promising use case for automotive assembly. Then we have factory palletizing. Then we have welding automation and healthcare robotics. Talking about the training, just to give you a short overview. So I actually trained for around 20,000 time steps, and I actually had like testing for 4,000 steps. And yeah, and then I just took these metrics into consideration, like the reward, like the efficiency, time, memory, convergence, stability, etc. Okay, so let's talk about the trajectory that we actually got. So basically, this is the classical RL that you can see on the left, and this is the quantum RL that is on the right. So basically, the triangles that you see, the red ones, these are the waypoints which I considered for the robot end effectors to actually travel on. So basically, the training part is there, and the dots that you see, the green dots and the darker dots, these are the points where the end effectors actually stopped, and they were traversing along the circular path. And the test is where the end effectors actually go. The darker lines that you see, these are just the end effector trajectories that have been traced in the circular path, so that's why it's a bit darker. And talking about quantum RL, you can see the same thing, but yeah, you can see the end effectors going quite near to the waypoint, which we'll see in the further slides again. And this is the test part where you can see the quantum RL is actually trying to make sure that the end effectors actually go in a circular path and go closer to the waypoints. So this is the KUKA robot where we're actually training our models on. So you can see it's actually trying to trace the path, but then yeah, it's just a kind of a small snippet of how it works. So it's actually trying to traverse along various shapes, like we do a circle, square, etc. And we are also trying in the future that it actually tries to trace complex shapes out of it. So you can just have a look. Okay, now let's go to a very important part, that is the comparative analysis. So basically, the average reward for classical RL was actually more than quantum RL. That is one of the analysis that I got out of it. Second is that the training and testing time of quantum RL is actually around 46.5% more than the classical RL, which is quite like almost like 50% more than classical RL. Then the latency part for classical RL will again here, like it actually takes lesser time to actually do a particular step. And for memory also, the classical RL is much lesser than quantum RL. And for stability, it's actually like this quantum RL is actually much more stable. When I say stability, it actually means it's actually earning more rewards in lesser time steps. So that's what quantum RL is actually achieving in this case. But the main reason why this is happening is because we don't have a quantum hardware. So basically, it would be really great if we have something in hand, which is a quantum hardware, where we could actually train our model on, and we can actually have a quick comparison. Because I believe that training on normal CPU or GPU is quite phenomenal for quantum hardware and quantum algorithms. And I think that having that would actually make our work easy, and comparative analysis is much more unbiased. So yeah. Okay, so our vision is that we are trying to make sure that quantum ML is not replacing classical ML. We want to make sure that they both work in unison. It is not a substitute to classical machine learning models. And also, we have to expand our benchmarking to large, more diverse data sets. The reason being, we are currently using smaller data set for quantum algorithms. But then the thing is that it's because of the lack of quantum hardware right now. So once we get a good quantum hardware, probably we could actually expand our data sets, and we can actually try to make it much more diverse. Second thing is we are actually trying to apply hybrid QML architectures, and especially in the field of healthcare, like it's one of my favorite fields because it's something that is directly consumer impact, and also we are trying to move towards automated quantum classical pipelines for scalable adaptive workflows. That is, again, as I already said, that we want to make sure that it is complementing classical models and it is not trying to substitute it in the future. And yeah, let's shape the next phase of quantum AI together. One thing is that I am going to again present the idea and my work in quantum effects in Stuttgart on 8th and 9th of October. So I would really love to have you there, and we could connect there as well, and we can also try to discuss more on the work. And also just to talk about our company, like what we are going to do is that we have actually partnered with Neura Robotics, and they are going to set up their Lara and Myra robots at our workplace. So where we are going to train our models on, again, like the classical and quantum RL. And maybe we can, in the next meeting, we can just talk about that more, about the results. Thank you so much for your time.